Okay then. So we know that we can do this. So we know what interval temporal logic is now. Now that we know, finally, let's talk about real data. Now you guys have experience with learning. You said that, right? What does your data look like? What did you learn from? What kind of data you learned from?
Using environment data.
Environmental data.
Samples of like pH in the soil.
Okay. A long time? In different...
Space.
Across space. So, well, actually, you probably got them in more than once, right? So, each one of the points where you took the sample got pH and something else that changed over time. So that's a time series. Am I right? Many time series. And they are also spatially related. Okay? Because they're not all close together. You want to know what happens in different areas. Right? What else? What other examples? Did you learn from what?
Some time series.
Time series of what?
Forest data.
Sorry?
Forest data.
Forest. Okay. So what was the attribute? What did you measure? What did data measure? The height of the trees? No.
No, basically force.
Force of what?
Like reaction force from your sensor.
Yeah. Sorry. Forces. It's not forest. Forces data. So you got sensors, and each sensors have different, measure something different, like acceleration or something. Okay. And you got many sensors, or more than one, and each one of them you collect the data for some time. So this is a bunch of time series, right? You got experience with learning? No.
Yes, so the cell boundaries for like a cancer growth.
Good. Those are images.
Yeah, images.
Good. Are they multispectral images, or you get only a few grades of gray, for example?
Or no, because they're from biopsies.
All right. All right. So those are images in which you got every pixel is got many numbers that determines its color somehow, and then you got a spatial distribution of them because they form an image. Yeah. All right. Experience with learning before? Yeah.
Well, this is not my problem, but I'm interested in spatial temporal data in soccer.
Spatial temporal data?
In soccer, like
in soccer.
X and Y for the players. And
Good. So this could be it is spatial temporal, but it is just like our first example. They say every player has got several attributes like X position and Y position that change over time. So basically, you can interpret this as a purely temporal if you wanted to, okay? Ignoring the fact that, and it's probably enough information that, I mean, what is we're trying to learn? Strategies, maybe?
like AI strategies or like players that sometimes are missed of the TV, so like you like project.
Yeah. All right. Let's see now. Do you think that if you take every soccer player and then you take all the information for one instance and you averaged in one number, do you think you're losing information there? Do you see that you average and you take just the average of the position? Is that informative enough?
I don't think so.
You don't think so? Okay. If we take the pH of every single point, and instead of seeing how it changes, we take just the average of the average pH over a year, are we losing information there? So, average is not the only thing that you can do, but whatever you do, when you push everything in one point, you're losing the temporal relation, right? So, if whatever you want to learn depends on how these things change over time, however feature we take to to take these numbers and we put them then together, we're losing something. Because if that feature is informative, that it would be more informative if we consider its temporal relation. So unstructured data can come up in many different ways. Temporal data is one example of what we call dimensional data, because it's in one dimension, but then, as I suggested before, you can say 2 dimension, 3 dimension to get images, to get videos that are images that change over time, and so you can do it in many dimensions. After a while, it becomes non-intuitive, of course. Graph-based data, like social networks, for example. Multi-textual data. Nobody has an experience in NLP here? No? Try that? Okay. So in that case, you would be tempted, of course you certainly did, use completely different tools because it's a completely different way, okay? You can't imagine, or you couldn't imagine, using the same tool to learn from soccer data than to learn from data. Are you with me? Do you agree? It's different tools, right? Well, no, it's the same tool, okay? You can use the same tool. How? Well, convert everything into model data. And this is one example, okay? So I'm giving you the example how to convert temporal data like time series, and I think this is the most common case here, into model data passing through interval temporal logic. This is not just theory. We did it many times in practice, and we didn't solve just any problem. We solved diagnosis problem, like taking the acoustic characteristic of voice, cough and breath, and see whether or not the respiratory infection pops up in the cough, like the doctor says, okay, like the doctor does. Or sensors from turbine, not just any turbine, Siemens turbine, or EEGs, electroencephalogram. Each electrode gives you an electrical signal over different frequencies, and you got many of them for a single trial. This is a multivariate temporal okay, data. Good. So seeing temporal data as model data is going to be easy. Seeing textual and graph data is not going to be so easy, and I just want to give you the idea. If we do this on a model, that is our data is only of one type, and we modelize it, we see how to do this now. But once we did it, modelize 2 different modes, it's going to be easy, right? Because if we can do it with temporal and spatial, then if your data is both temporal and spatial, you got 2 different frames, okay? I didn't tell you how to learn from 2 different frames, but we can do it, okay? And we'll go over it tomorrow. So let's focus on the case of time series, dimension 1. Only imagine that our instances are multivariate, like they are in any case, but they're they're only temporal data, like this one. Your data look like this one, right? So this is the x and this is the y over time. For example, your data look like this in the same way, and yours too, right? These are the value of each sensor. Concrete representation. How do we represent it? We got an RFF or we got an Excel, all right? So pH changes over time in the instance 1, measuring point 1 or player 1 during this particular match is got these values. And then Y or acidity or whatever it is, the other sensor number 2 goes like this, right? So this is how you present the data. Concrete data are numbers. In the temporal case, they change over time. I can assume that all of them have the same number of points. We did this assumption before, remember? So your sensor, you measure of the same number of data points, right? Build all the intervals that you can on the points that you have, and compute all Allen's relations between them. And now what is the attribute now? How can they be extracted from the value? Well, actually, we already said that when I asked you guys, what if we average everything? And you said, we're losing information. And now I say, take the same function and apply it to every interval, because every function that can be applied on the whole series can be applied on pieces of the series. Now, because you got your literature, you know that somebody else has already discovered that for your specific problem, that specific feature function makes sense. Say in soccer is the acceleration. In your case, is the maximum of the temperature of whatever, or the forces of whatever, okay? Or maybe is a very complicated function, the number of peaks, or the average the average value of the discrete derivative. You don't have to discover this. Somebody else already did. What you have to do is apply this to every interval, and so formally take a feature extraction function from a set of functions, the set of my features. Function can be taken from a classic function vocabulary, including average, minimum, maximum, or very complex one. How complex? Well, as complex as you want. It may not have even a name. It may be a neural network. Take a neural network that works on time series, apply it for feature extraction to every interval, and you got exactly the same picture here. And what are you going to learn? The relationship. So a function f applied to a variable v, so f of v becomes an attribute. The set of your functions is your problem. It's not my one. It's not my problem. You decide. And then you got your Kripke structure. Take every interval, and every interval becomes a world. Apply feature functions, so now the word can be labeled with numbers exactly as we had like before. This looks exactly as a model instance as we were discussing yesterday and today, right? But now you can learn from it. So in general, what we have here is the concept of transformer. What is a transformer then? It's a function that takes a model data set, a logic, and a set of functions, and say, okay, use these particular relationships. I said before, we introducing the temporal case with Allen relation, and then I said, well, we know the language that doesn't have all the Allen relation. It's easier to understand if you only use during and overlap, for example. So let's only label using an overlap, during an overlap if you want to. And then in my problem, the number of peaks and these other functions are really important. Let's put them in the mix over here. Let's put everything together to get one thing that looks like this. Now you do this for every instance, and you get a model data set. Then is a label model data set, and you can learn. What can you learn? Well, it so happens that it isn't the fact that it isn't the average speed of a player, but it is the average speed of a player while the other player does like this. Or it isn't the number of peaks of the pH, but it is the number of peaks of pH before the number of peaks of whatever, what really makes the difference. Whatever it is, if it is qualitative, we can pick it. We can pick it up. All right? So given a data set of unstructured instances, given a specific model logic that it wants to use to structure information, and given a suitable set of future instruction function, one immediately obtains the version, a model version of the original data set, as we did in the temporal case. What if the information is not purely temporal? All right, we got the images. Somebody got images here. Okay, so take the image, the interval becomes an hyperinterval, in this case a rectangle, and then apply what is important, how dark it is. Well, let's say how dark it is a new function, and you get all the rectangles with the number, with the evaluation of how dark they are. And now that it so happens that whatever it is that we want to learn from, it doesn't depend on how dark the whole image is, but it depends on the fact that there is a dark patch within a less dark one. Now we can pick it up. So you can do this for dimension. What happens if you do dimension 0? Well, dimension 0 is just tabular. So in this case, and actually in every of the one, the bottom one is the original propositional learning, exactly as we had before. Now, so the dimension 0 is a special case of dimensional data. So now the subgroup of dimensional data that include images, video, and so on can be treated in a completely uniform way. Is this the only way to modelize data? I said it before, it's not. If you want to modelize it by using point-based temporal logic, only the model one, not the until, for example, you could do it. But does it make sense for continuous data to look at single points? Maybe in some problem it does, but in general you can say it does not. So, but you in general using different model language give rise to different model data set, and probably the information is clearer in one case than it is in another. This is part of the pre-process. We all do pre-processing learning, so this is just another way of calling pre-processing. The logic that we use in dimension more than one is the same logic, only in the multidimensional case. So rectangles can be related by 169 relations, but then he says, no, I like topological relations, and then they are definable within. So just put them in the surface. So let's define what it means for two rectangles to have one point in common, okay? And so you got many less relations, 8 of them in the RCC8 algebra, or even 5 of them. I don't know if you know the several versions of there are several versions of that. And you got a new logic that it is definable within the original one. That is what I say when I mean when I say the original HS logic, the interval temporal logic, is almost everything you need, almost, because you can define everything within it. So there are different flavors of topological relation. Other cases that are not dimensional, that means that you cannot reduce them. For example, text. Okay, let's think about text now. You said you have experience. What is text? Text is, what is a text? A text is a succession, is a sequence of tokens. Token can be words, token can be part of words, token can be even sentences if you want to do. Usually we take word as a token, all right? So you can put them in a linear order, and you got word 1, word 2, word 3, word 6, right? Now, take anything you know about extracting information from a text. Let's say, I don't know, a topic modeling problem, right? So you got your Python package. You don't have to write it. It's already there. A Python package that, given a text, it gives you a bunch of topics, right? You know that it exists. And what you can do is try to classify your text as, I don't know, this is an email that says something about an insurance claim, or this one is an email for protesting something else, okay? So say your problem is classifying these things, and you got this tool that is, you didn't write it, it's nothing to do with us, but you got this tool that, given any text, it gives you the bunch of topics. And now, here's what I say. take any pair of words and it becomes an interval. Between an interval, there's a text. This text can go through your topic modeling, and now you got every possible pair of tokens labeled with the topics. And now it so happens that your class is defined by the fact that topic 1 is spoken within topic 2. And then the opposite of your class is got topic 1 and topic 2, but separate. It's a model, right? It's a model problem. Okay, so you have only to pick up this. So what we did is modelize text. You don't like topics? Well, if you don't like topics, I'll tell you something else. What are large language model based on? What is the one engine that makes LLM possible?
Transformers.
That's right. Transformers is Transformer is the top. I mean, I was talking about interpretation. What is the do you know about it, embedding? I'm talking about embedding. Okay. Do you know what embedding is? Several dimension embedding. Do you know this idea? LLM works because every token goes into a multidimensional space of many dimensions, many numbers, okay? And this has been done in a statistical way so that it's got some properties that says that the 2 points close enough in this multidimensional space means similar things, okay? It's a semantic embedding, right? You didn't know that, okay? But the point is that there are so many people working on embeddings, and if you want, take your favorite embedding, transform your text in a sequence of numbers. Now, every dimension is a different attribute. Every value on this attribute is one value on the dimension, and now your text is a temporal series. Take your temporal series, pass it through this, and you got a model version of your text. So you can do this. We did this. At least we are trying to do this. The principle then is the same. Text is linearly ordered, words or other tokens could be pointed in linear order, intervals are determined by pair of points, and then feature extraction function can be NLP, any NLP function, even a non-interpretable ones. It doesn't matter. When I mentioned that feature function can be non-interpretable, and what I mean is that what I'm getting to is a neurosymbolic situation, a neurosymbolic setting, and therefore maybe it so happens that in your case some say predetermined or pre-trained neural networks is so useful that you don't want to get rid of it, and yet you're searching for interpretability. One way to go towards it is this one, okay? Don't get rid of it, but then study the relationship of how it is applied to different parts of your instances. Interval temporal logic such as a yes could cover the case of text data as well. Other characterization, of course, are possible. Graph data has not been studied. We didn't get that. We have some ideas of how we can do it. And of course, a graph is already, you can already see a graph as a cryptic structure if you wanted to. It's not that easy, but you could do it. So I'm mentioning here all the publication we already have on all these kinds of this case, and this is the last thing, just a summary. So I hope I fulfilled my promise. I promised yesterday morning that by the end of business today, we would be convinced that learning model formulas make sense. I hope I convinced you that it makes sense on the practical side. It so happens that learning model logic formula also makes sense in the theoretical side, because model logic has been studied so long and for so long, and it has been studied, but then applying in it is not that easy or it wasn't that easy so far. Now what we did, or I like to say we did, we made it possible. So we made it possible for anyone to come up with a model logic that likes, and he likes his properties and expressive power, and it does exactly what you think it does. And now what do I do? Well, if you write, then you can see some data in Modely. We got the tools for that, and then you can learn model logic formulas in your language and see what happens. So this is how what I like to think we've done, and we're very proud of this, I have to say. We are one step away. I mean, speaking among us, I mean, we're one step away to make this real, in the sense that we said it the first day, yeah, well, we like decision trees, but decision trees alone are still somehow, a toy. How do we make this real? Then we gotta be able to learn from multi-mode data. We gotta be able to learn efficiently, and we gotta be able to learn ensembles of these things. We gotta be able to see how the formula are, to work with them. We covered this tomorrow. It's gonna take just 1 hour or something, and then everything else is gonna be hands-on. No, that's on, but Giovanni is gonna show you some of these cases from the beginning to the end, to see this is not just words, in the air. Okay? Thank you for bearing with me, and we'll see it again tomorrow. Thank you.